I'm going to start putting up, you've got the last stuff, right? You get the assignments from concavity and second derivative test. There's one assignment that's just basically, you have to just study graphs, graphs of derivatives and kind of just analyze graphs. Not really, I can't remember if there's any, I don't think there are any problems on that one where you have to actually do calculus. And then there's another one where you're making tables and you're finding concavities and inflection points and stuff. And you're graduating to kind of the last thing we do before we jump into optimization is just analyzing functions. So it's just going to be sketching functions. And there's going to be 3 assignments. I'll just give them to you, one a day. The first one only has 1 real problem on it. The other 2 each have 2 real problems, or other 2 each have 3 real problems on them. So what those are going to be, you'll see when you get there, they used to be really tedious problems that I about got lynched for putting on the assignments because they took forever. Because if you got one little part wrong, you'd have to redo it. They were ridiculous. So what I did now is I put the same problems up there, but I rewrote the questions so that it's up to you to just make a table and do the questions and then just check off that you did them. Okay, but you need to be able to do that. You need to be able to make the tables and sketch the functions and answer the questions about those, because that's what the next test will be. The next test is going to be a paper and pencil test where I'm going to give you some problems and I want to see the tables. I'm going to grade you based on the tables and your ability to use the tables to answer questions. Okay, that's what it is completely. So you got to get some good authentic practice by making the tables on these assignments. Okay, does that all make sense? Okay, so go. What do we do here? What's the domain? 0 to 2 pi. There you go. Okay, so we can go. Okay, that's a good kind, right? It gives you the domain. Now what? We need derivatives. What about, okay, let's talk about symmetry for a second though. What about the symmetry here? Does it have symmetry or not? It doesn't. But how do you know about the cosine part? Like if we wanted to explore the symmetry of this thing, I'm going to do this on a separate page because I don't want to. Okay, there's f of x, right? Think of that as being f of x. What's f of negative x? What's the first term going to be? Yeah, negative 8 radical 3x, right? Plus 16 cosine of negative x. What's cosine of negative x? So what we're asking, I guess, is the question, is cosine an even function or an odd function? Right? It's even, but why? There's a couple ways you could pretty easily convince yourself of this. One of them is, think of the graph. If I graph a cosine function, if that's 1 and that's negative 1, what does cosine function look like? Where does it start? Does it start at 0 or does it start at 1? It starts at 1, yeah. And it does that. What kind of symmetry does that have? Does it have rotational symmetry about the origin or reflective symmetry about the y-axis? Reflective. That's even symmetry, right? So this is cosine x. Where does sine start? 0. Right? So it's going like this. Does that have rotational or reflective? Rotational. So what kind of symmetry does sine have? Odd. Okay, good. I think an even better way is going back to my very favorite thing in the entire universe, is you all know the unit circle, right? On the unit circle, if you think about an angle x, so that's x, right? Then so if I look at these ordered pairs, what comes first, sine or cosine? Cosine. Right? If I go down to negative x, what do you notice? I get the cosine of negative x. I gotta write that better. The coordinates of that point are going to be cosine of negative x, sine of negative x, right? Okay, but look, the x coordinates are the same, aren't they? Everybody see that? So what's that tell me? That tells me that the cosine of negative x must equal the cosine of x because they have the same x coordinate, right? In quadrants 1 and 4, the x coordinates are the same. How about the sines? They're opposites, right? Whatever that amount is, that's negative the same amount, right? So this is telling us that cosine of negative x equals cosine of x, and sine of negative x equals negative sine x, isn't it? Everybody agree? You see those relationships? So you can also just show that on the unit circle, that cosine is even, sine is odd. Okay? What would tangent be? It's going to be odd. How'd you know so fast? You're right. Yeah, because it's sine over cosine, so I'm going to get odd over even, which makes odd, right? Because we treat odd like a negative and even like a positive, and we use our quotient, our sign rules for dividing, okay? All right, so back to business here then. So this thing has no symmetry, does it? Because that's an odd term and that's an even term, so therefore it spoils the symmetry. If that had been sine, this whole thing would have been odd. Okay? So we need a derivative though, don't we? Let's do y prime. Okay, so what is y prime equal to? What's the derivative of the first term? 8 square root of 3, right? Because the derivative of x is 1. How about the second one? What's the derivative of cosine? Okay, good. So then minus 16 sine x. Agreed? Okay. When is y prime equal to 0? Okay, but you can give me something simpler. Like I just want an equation when what equals what? This thing equals 0 when 16 sine x equals 8 radical 3, right? See what I'm saying? Okay. If I set that thing equal to 0 and solve, whoops, 8 square root of 3. So to solve for sine x, what would I do? Right? So sine x equals square root of 3 over 2. Huh, what do you know? That's a convenient spot for us on the unit circle. So where does that happen on the unit circle? Where is sine equal to square root of 3 over 2? Sine is the vertical or horizontal coordinate? Vertical. So where would sine equal square root of 3 over 2? That's the big interior coordinate, right? So is it going to happen here, here, or there? There. And where else? What other quadrant? In what other quadrant would the y coordinate of a convenient point be right there? Yeah, right there in quadrant 2, wouldn't it? So what angles are those? What angle is that? pi over 3. That's 60 degrees or pi thirds, right? What's that one? What is it? 3 pi over 2 or 2 pi over 3? Yes, 2/3 pi. So those would be my two interior critical numbers for the first derivative, right? Everybody get that? Those are the places where the first derivative is equal to 0. So x equals pi thirds or 2/3 pi. So we need to add those to my chart. Okay, so if that's pi, it's going to be about there. Actually, I did that wrong. I want to put it probably like right, more like right there. And those are zeros of the first derivative. So what do I know about those places? Horizontal tangents. Okay, what else? Now what? What should I do? Second derivative, yeah, right? And let's just assume we have to find everything for this. So we need a second derivative. Okay, second derivative is actually easier though. What is the second derivative? Right, because that's derivative of that first term is 0, right? It's a constant. So I'm just going to get negative 16 cosine x. Now where is, the second derivative is going to equal 0 when cosine equals what? 0, right? Because I have to multiply negative 16 times 0 to get 0. So y double prime equals 0 when cosine x equals 0. Well, where is cosine is x or y coordinate? So where is that equal to 0? 0, pi, and 2 pi, exactly, right? 0, pi, and 2 pi. But 0 and 2 pi really aren't critical numbers. How come? They're endpoints, right? Okay. So I'm going to check them anyway, because what are we trying to do? We're trying to, well, I guess, yeah, we're just trying to sketch this thing on that interval, right? So then I've got the interior critical number pi, which is where the second derivative is 0. And if I want to put that there, I can too. Okay, so now what do I need to do here? Which row am I going to work in? Oh, whoops, you're right. No, you're absolutely right. It is. Yep. It does matter. It absolutely does matter, and it goes there. Okay? So now what? Say it again. Oh, shoot. Yeah, we did that wrong. We did that wrong. Yeah, where should those be? Yeah, they shouldn't be there, right? Where should they should be? The cosine is the x coordinate. That would be here and here, right? Okay. So our green points would be, what are those? Pi halves and 3 halves pi. Okay, good. So pi halves does go here, and 3 halves pi goes there. And those are zeros of the second derivative. Okay, so now, finally, we got that right. So now, which row are we going to want to work in here? Bottom one. We want to work in the second derivative row. And what points are we going to test? Because we're going to kill two birds with one stone here. We're going to figure out what are those first derivative critical numbers, what's happening there, And at the same time, we're going to figure out if we have inflection points or not, right? Okay, so I'm going to check my first derivative critical numbers. So let's do this too. Let's remind ourselves. Those are first derivative critical numbers. Those are second derivative critical numbers, right? So let's evaluate our first derivative, or excuse me, our second derivative at pi thirds. Well, that's easy to do. Negative 16 times the cosine of pi thirds. What's the sine of cosine pi thirds? What quadrant's that in? 1. So what's the sine of cosine there? Positive. So I get negative times positive is negative, right? So what's going on there? What's the second derivative test tell us? That is a sad function, right? That one is concave down, so it's a maximum. How about at 3/2 pi? 3/2 pi is in, or sorry, not 2/3 pi. 2/3 pi is in what quadrant? What's the sine of cosine in quadrant 2? Negative. So I get negative times negative is positive. And so I'm getting happy function. I'm getting a minimum there. Okay? What's going on here? Inflection point. Okay? What's going on here? Well, we don't know. How would we check? Pick a point on the other side. 2 pi was a zero of neither derivative. It was a critical number of nothing, right? So let's just check our endpoint and just see. We could take the sine of the second derivative at 2 pi because it's so easy to do. Well, what is the cosine? We're going to check the second derivative. What's the cosine of 2 pi? 1. Yeah. So I'm going to get negative here, right? What's that make that? Inflection point. Okay, and then at 0, 0 is the same as 2 pi on the unit circle, right? So I'm going to get the same thing. I'm going to get negative there also. Oh, I didn't even need that one. Never mind. Right, because I already have a test point to the left of that second derivative critical number. I only needed to check, all I needed to do to figure out what was going on here is I needed a sine of the second derivative to the right of 3/2 pi in our domain. Everybody get that? Okay? So that's everything I need to know. If I wanted to really anchor this thing down, I would want to get coordinates of all those interesting places. And so I would just evaluate my original function at each of those, at the endpoints and the first and second derivative critical numbers, right? Which we can do if I just happen to have what are the odds? I just happen to have a function built to do that. Okay, and so if I evaluate the function like at 0, I get 16, right? So I need a 16 there. If I evaluate the function at what else? Pi thirds. I get roughly 22.5. Oh, I can't do that. That's not going to work. I got to write this. $22.5. If I evaluate it at pi halves, I get 21.8-ish. If I evaluate it at 2/3 pi, I get about 21. Three halves pi. Ooh, I get about 65.3. And at 2 pi, I get about 103. So I could make those into ordered pairs, and if I do that, there's what my graph looks like. Okay, does that make sense? What are the coordinates of that? Look at that. Pi thirds, we get a, didn't we say we got a maximum there? 2/3 pi, we got a minimum. This thing won't show me points of inflection, but doesn't it make sense that somewhere in the middle there between, the inflection is going to change from concave down to concave up? And then I get another inflection point up here where I'm changing from somewhere like right around, I don't know, like right about there, changing from concave up to concave down. Okay? So it all makes sense. This fits what we said it had to do. Okay, for your notes, there's a picture. Okay, let's try this one. We'll just kind of work through, I just pick a bunch of examples out that you kind of need to see, so you know how to deal with different kinds of functions. So how about this one? We need a first derivative, yeah. Okay. What's our domain going to be on this one? Well, okay, there's a part of this that's going to limit the domain. There's a factor in here that's going to limit the domain. It's going to be all values greater than 0. We don't include 0, right? Because what is the domain of a log function? It's only the positive numbers, right? Positive real numbers. So the domain, we know right away, is going to be that, right? Okay, so could this thing have symmetry then? Can't have symmetry, right? Because the only kind of symmetry, look at these other, I have x squareds in there which are even, right? But the domain starts at 0, so we can't have symmetry, right? This thing, you can't rotate this thing about the origin or reflect it about the y-axis if the graph doesn't include x equals 0 or less, right? So no symmetry. Okay, so we need derivatives, don't we? Yeah, let's take derivatives. First derivative. Okay, how am I going to differentiate that first term? I'm going to have to use product rule, and let's divide it up like this. Let's go ahead and just put all this stuff together as one factor. Okay? So what's that going to give me? First times derivative of the second. So I get negative 2x squared. What's the derivative of log x? 1 over x. Plus second times derivative of the first. What's the derivative of the first? Negative 4x. Good. So there's the derivative of the first term by the product rule, right? And then we've got plus the derivative of the second term is what? 38x. So we need to clean this thing up a little bit. Negative 2x squared times 1 over x is what? Negative 2x. Minus 4x log x plus 38x. If we combine like terms, don't we just get f prime of x equals 36 x minus 4x log x. Agreed? Okay. Okay, and they want us, would we probably use the second derivative? If we were just looking for extrema, would we use the second derivative test here? Probably not, right? I mean, that's kind of a hard derivative. I've got another product rule in there. It's just a lot of algebra. So we probably would just use the first derivative test. Let's pretend like we're trying to find everything here, though. We want to sketch. So we need everything. So we need a second derivative. Maybe before we go any further, though, let's go ahead and find our first derivative critical numbers. Okay, any place where our first derivative is going to be undefined in our domain. Remember, our domain is the open interval from 0 to infinity. So there's no place where the derivative is undefined, agreed, in our domain? But we got to find out where it's equal to 0. Okay, so okay, we've really got to do, well, let's factor this thing instead. What could I factor out of each term? I could take out a 4x, and what's left behind? Okay, so I'm finding the zeros. So f prime equals 0 when what? X equals 0. Or what? Say it again. How'd you get that? Well, I've got to set that factor equal to 0, right? So let's not try to solve for x yet. Let's just isolate log x. When log x equals what? 9, right? Okay, now we can solve for x. Log x equals 9 when x equals what? How do I undo a natural log? Base e exponentiate, right? So x equals e to the 9th. So those are my two critical numbers. Okay? E to the 9th, does that one kind of make you nervous? Okay, don't. It's just a number. It's just a number. Just a number. It's just going to go, I mean, it's an exact way to write the number, but we could put it in a calculator and just get a decimal approximation. It's just some number, right? Okay, so now we need a second derivative. Okay, second derivative. We'll differentiate term by term. What's first? 36? Okay, now this one's going to be a little bit of a pain, right? We're going to subtract, and now we've got to do product rule, right? So I've got 4x times the derivative of log x. What's the derivative of log x? So I've just got that, don't I? Right? Plus log x times the derivative of 4x. Isn't that just 4 log x? Right? And those cancel, right? So if I distribute that negative over that product rule that we just did, we get the second derivative equals 36 minus 4. That's 32 minus 4 log x. Right? Okay, so if we want to set that equal to 0 and solve, don't we know that the second derivative equals 0 when 4 log x equals 32? which is the same thing as log x equals 8, right? So what's my second derivative critical number going to be? E to the 8th. Okay, so in our, we can make our table then, right? We know we're going from open interval from 0 to infinity. We had first derivative critical numbers at, oh, do both of those count? Look at our first derivative critical numbers, 0 or e to the 9th. Are those both in our domain? 0's not, right? We have to toss 0 because that's outside of the domain. So the only one we get is e to the 9th. So out here we've got this big number e to the 9th, which is a 0 of the first derivative, so it's a horizontal tangent. And is e to the 8th greater than or less than e to the 9th? Gotta be less than, right? How much less? It's a factor of e less, isn't it? Yeah. So what should we do? We got to analyze this thing. I got to know what's going on at e to the 9th. So yeah, we need the sign. We'll use the second derivative test. We need the sign of the second derivative. Okay, so what is f double prime of e to the 9th? Well, that's going to give me 32 minus 4 times natural log of e to the 9th. What's the natural log of e to the 9th? 9. Yeah. So that gives me 32 minus 36, which is negative. Right? Everybody see that? You can see how we get that, right? Because a natural log undoes an exponential, right? So that just gives me 9. Okay? So what's going on at our first derivative critical number at e to the 9th? Yeah, it's sad. So it's a peak, right? It's a relative max. So what's the other thing we need here, though? What is this? We don't know. So what do we need? We need a test point. We could do e to the 7th. We could do. How about if we just do e to the 1? We'll pick an easy one. E to the 1. So it's going to be positive, isn't it? So f double prime of e is going to be 32 minus 4 times e to the 1 is just 1, right? 32 minus 4. So it's positive. So what does that make that? There it is. Okay? And if we wanted to, like we could, what's our original function right there? Okay, so then I tell you what, I don't want to, that limit at the end, what's going on at infinity? If I take the limit of this function as x approaches infinity, what's going on? It's going to be infinity, right? So we could do this. The other limit's kind of tough. The limit as x approaches 0, that's going to give us an indeterminate form of a kind that we're not used to, right? And did we do any like, I guess we did, didn't we? We did some like that because you guys made it, you were able to split that and make it a ratio. So let's do that one. Let's do the other limit. What's going on at this end? This is a good example. The limit as x approaches 0. All right, so ooh. Okay, so for you guys to be able to do limits, right, the only indeterminate forms we learned were 0 over 0 and infinity over infinity. There are others that we'll maybe get to at the end of the year. But this does not look like that. This looks like 0 times negative infinity, right? If we approach 0 from the right, from within our domain, that log function is going to go down to negative infinity. So what do I have to do to this thing to make it a ratio of either zeros or infinities? What could I do? Let's just say I leave the log, I'll leave the negative 2 log x on top. What do you think?
Separate the limits?
Say it again?
Separate the limits?
Well, you can't make them we have to make it we can't make them separate like a product of limits or something. We need to make it a limit of a ratio. But x squared is the same as 1 over what? X to the negative 2. So it's x squared is the same as 1 over x squared, right? So we could rewrite this as the limit of negative 2 log x over 1 over x squared, something like that. Make sense? Okay, now what indeterminate form is that? If I let x approach 0 from the right, isn't that giving me negative 2 times negative infinity? So that's giving me infinity over infinity, right? So that's an indeterminate form to which we can apply L'Hopital's rule, right? It's infinity over infinity. So what do I do with L'Hopital's rule? Separately differentiate the top and the bottom. What's the derivative of negative 2 log x? Negative 2 over x on the top. What's the derivative of, on the bottom we have x to the negative 2. What's the derivative of x to the negative 2? Negative 2 x to the negative 3, right? Good. So on the bottom we're going to get negative 2 over x cubed, right? Pretty good. Okay, so now this time let's go ahead and remix those and evaluate what we get. So if I multiply by the reciprocal of the bottom, the negative 2's are going to cancel. And we're going to get the limit of x squared, aren't we? Well, what's the limit of x squared as x approaches 0 from the right? Is that indeterminate still? What is that? 0. Yeah. Okay, so we know that the limit of this thing then, as x approaches 0 from the right, is 0. Okay? And if we want to look at this function, what's it look like? And if we really wanted to pin this thing down, I would just plug those values into the function, right?